Okay, for people who are joining this live stream, this is a continuation of our discussion of multi-computation and extending our whole computational framework to think about multi-computation. And we've got multiple different things to study in terms of multi-computation. We had been actually yesterday in a different meeting discussing the generalization of our find equational proof technology. I want to let me just try to make several different buckets that I wanted to make sure we talked about today. I want to talk about, okay, so just as a sort of proto thing, I want to talk about supplied, whose name I don't really like very much. That hasn't grown on me since yesterday. I want to talk about that. I want to talk about infinite lists. I want to talk about representation of proofs, and general tracing of computations. Those are topics there. Let's save this away here. Okay, so actually one first thing, this is a point from Sander by email. Sander points out the very obvious issue of when we have, so let's start off talking about supplied here, that when we are doing a map with a supplied and there is a map within that, there's a question of which, let's see, how does it work here? There's the question, just like variables inside a map, just like if you have a map where you have, hash plus map, blah, blah, blah. And the question is, which hash are you picking up? And it's always the innermost hash that you get at any given, well, not in that case because I didn't have another ampersand. But the question is, for supplied, are people understanding the issue? I mean, let me pull up Sander's example here. Okay, what is this? So this is, I see. So the issue there is within that supplied, if it has a hash index, that is presumably getting the hash index from the map. And Sander asks the question, which I think is going to get kind of messy, about scoping of this. And is there a way to reference the outer index here? How would you reference, in this kind of setup, how would you reference the outer index?
So I think that the long-winded way of writing it would be for the outer, you'd have to have an outer supplied for sure. Yep. And then one way you could do it is that inside that outer supplied to use function, right? And you give it a name. In that case, it would give you the whole association. And probably what you'd have to do, excuse me, just to make it, better performance and things would be to also give it a first argument to supplied.
Yep.
To specify which keys you want.
Okay.
Yeah.
And then here, well, I don't want to.
Well, now you have to say x comma I or something.
Right.
Because you're going to get two arguments.
Okay. And then in this case, that is the, okay, so then here I can say I plus index, for example.
Yes.
Right.
Mm-hmm. And don't forget the inner map, of course, has to be mapping over U.
Inner map.
Oh, assuming that's, oh, never mind. I thought you were doing something slightly different. Yeah. Okay, fine.
Okay. So that's the inner map. And that closes the function. And the supplied has that function inside, and that's the table. That's not grotesque. I mean, it's the same as what
you'd have to do. Does supplied even work in table? Like table doesn't take a function. Maybe it works in array.
Yeah, well, right. But the thing is, we want supplied to work in rules in particular. So that's a good question. Should supplied work in table? It would be nice if it did. Monitor works in table.
Well, so
No, a
the
monitor
question
works in
is,
table
should
'cause it's-
supplied be specifically for functions, or do we want it also for rules and maybe other things?
Well, that's a good question. I mean, supplied in table, rule, etc. I mean, we want something like it in all those places
I strongly think that table doesn't make sense.
because you say you've already got the variable.
Well, you've already got the variable, and the reason module works or monitor works is just because it's
Picking up the variable.
It's picking up the variable. I mean, it's just because table uses block basically. But I think that, like, for example, with rule, you can at least make an argument that, well, the right hand side of your rule delayed or something is a little bit like the right hand side of a set delayed in a function, and so it's at least like the syntax is basically the same. But in a table, there's no function anywhere. Like there's no, yeah. I mean, there's no, yeah.
So certainly array, but not table. So you're saying replace this by an array, and now this thing here becomes
right. So now the U, you do range of U inside, and then on the outside you just do range of 10.
Right. Right. Okay.
Actually, just 10.
Yeah, just 10, right? Because it's just the array thing. Okay. So how does this potentially solve the problem of monitor inside map? The supplied thing?
So I think it's kind of reversed. Like the progress indicator would use supplied for its implementation.
I see. So does that mean monitor of map? Because what we've wanted it to do is to just be able to say monitor of map without a variable. Am I making sense? Does this provide an implementation for that?
Not as such, but for things like fraction complete.
Yeah, but how would that work? I mean, is that, can you see how?
I'm confused. Are you asking how are we going to implement the progress reporting for map?
Yes.
Or are you talking about?
Yes, that would be.
I mean, I feel like that's going to be a lower level thing. I mean, I think if we did it in the top level using something like supplied, there'd probably be a performance impact.
No, I understand, but can we at least conceptually see how it would work with supplied?
Well, I mean, one thing you could do is just have. I mean, I guess you do module, or like this is what the monitor would kind of turn into, right? It would be module of progress or something, fraction, something like that, and then you have inside you have map of right supplied, and then you want to get the value, and then you want to get the fraction complete.
Okay.
Or it would be like index. And then you would use the index from the outside to build a.
Well, let's say we've got fraction complete. Let's imagine.
Yeah, supposing we have fraction complete.
I don't know that you would have fraction complete in supplied, so much as you calculate the fraction complete using supplied.
We've been talking about having that as a possible key, fraction complete. So let's just assume we have fraction complete as a key.
Yeah, I mean, worst case, it's not hard to compute yourself, but yeah. So you just say supplied, and then you'd say quotes fraction complete right there.
Oh, quotes fraction.
Well, actually, I guess you could write it. You could write it like this actually, if you want to use. Yeah, so you'd say progress equals fraction complete semicolon semicolon f of hash expression, and then of course you're going to need parentheses and an ampersand, and then inside the module, but outside the map, you'd write monitor. Right.
There, you'd monitor the progress. You'd monitor the assignment of progress.
Yes.
Right. Makes sense. Yeah. Okay. So look, I think even though supplied is not a name that's been sitting well with me, It sounds like Ian thinks, Ian is pursuing this. Is that a fair statement?
Yeah, I can come up with like a list of keys for structural and tree type operations.
Good, and functions that they should go into, and then we have to start thinking about how the actual implementation works, and whether we can do at least an initial implementation without values and so on. Okay, topic 2. This is already an exciting topic, and okay, actually, the another issue is how to deliver structured sort of supplied material. So this is what we talked about before. You're deep in a computation. You are throwing sort of information about what's happening in the computation. It's like AKA modern trace. Okay, so remember, you're iterating through a computation. You're recursing through a computation. And we've got these two different forms of progress in a computation. One is recursion through the spatial structure of an expression tree. The other is essentially time-like recursion of reevaluation of things. Right, so it's like spatial recursion and temporal time-like recursion. And this is both are throwing up results. Okay, so the question is, how do those results land? What do they land in? And that brings us across here to this equational proof thing, I think. Does this make any sense to people? I mean, we're trying to say you're doing a computation and things are happening, and you want to record what did you do in the computation. Anybody understand what I'm talking about? Anybody want to try re-explaining that in a different way?
It's like the difference between fold and fold list, maybe? Like fold, you're just getting the final value. Fold list, you're showing the steps along.
Yes, that's a good point. Yeah,
like very generally.
Right. Okay, right. That's a good way to think about it. What is the general version of quotes nest list, as opposed to the evaluator, the main evaluator, which just gives the result of nest. Okay, so let's take an analogy here of full simplify versus find equational proof. So full simplify just tells you, yes, this result is true, but find equational proof shows you the steps that got there. Okay, or in particular, if you have something which eventually reaches a fixed point. Okay.
I think I disagree slightly here. So trace already separates these two types of recursion, but one is different elements in a list. The other one is nestings of lists. Now, the thing that trace doesn't give you that find equational proof does is what got applied so that you arrived at this new expression. You just get the new expression, but you don't know how or why.
That's correct. Right. And in this picture of find equational proof, these events here, this shows you the new expression. And this event shows you is the melting pot that took the existing expressions and turned it into the new expression.
Right. But
and in trace,
in trace, we already have the sequence of what happened.
Fair enough. Yes. Okay. So trace gives sequences of results and a skeleton of, quote, spatial recursion, just in a list, right? Is that right?
Yes. I would argue that also the time-like recursion.
But that's its sequence of results, right? So let's do an example. Can we do an example? How can we do an example of trace? Let's see. How would we do this? We would say, well, let's just do something here where we say nest fx3.
Well, do some mathematical operation that gets recomputing something.
How would I do that? Can I do 1 + 1 + 1 + 1? Or is that also going to be trivial? How do I do something that's non-trivial? Maybe I can do the, maybe I can create, what could I do? I could do a fold list of F, and then I could do table of 1, 6, for example.
Can you define for perhaps one of these factorial definitions, and then we evaluate it?
Okay, what would happen in this case? What would happen here? If I take this thing here and I say trace of that / dot F goes to plus. Is that going to be interesting? Yeah, that is mildly interesting, right? Look at that sequence there.
Yes, but here we have also the nesting, which I think is the interesting part. What you call time-like recursion.
Is this time-like recursion?
Well, perhaps I'm confused with parentheses. It's very small.
Okay, but hold on, I can make it bigger. That's a problem that's easy to solve relative to all of the ones we have.
Yep. So look at the big set of nested lists where,
yeah. What am I seeing there?
So 1 + 1 evaluates to 2. That expression evaluates to 2 + 1.
And then, but then we're using, this is some kind of weird space-time thing, because then we're using the outer +1 is being introduced.
So the sequential thing is an expression got reevaluated, and the nested lists are sub-expressions got evaluated.
I understand, but how do we do a pure, the same expression got reevaluated many times? Is there a way to do that, to see that in trace? The heck is this? Okay, so let's say trace, and then let's say, I see it. I equals 1, do I equals I + 1. You know, this hasn't been modernized since we changed the syntax for trace, for do. Okay, there we go. Oh my gosh, can anybody explain to me what the heck is going on here?
What's the first element? It's hard to tell with the line breaking.
Well, let's
they
do
may
this.
say column of that.
Fine. Let's do this. Let's say framed. Yeah.
Okay.
Actually, you know what? Let's do this. Let's map framed onto every level that is a list. Okay. Map if head of hash triple equals list, framed of hash, otherwise hash. And then let's do that. Let's do a map all of that onto the trace.
There's
what the heck is that? Did I make a
form or something like that? Maybe. Maybe you
should
use
right.
You should use replace all, or you should use replace with level spec 0 to infinity.
Well, I think the real problem is if head.
You're mapping into a hold form ultimately at some point.
Yeah, I know.
It
really
doesn't matter what you write.
1, 0.
No, the if isn't evaluating because it's inside of a hold form.
Oh,
it doesn't matter what you write there. Just use replace. Just use replace and just say replace, and then your trace.
Wait a minute, replace all.
No, replace, because you need to do from 0 to infinity, because otherwise it'll only do the outermost level.
Okay. So what do I do here? The if hash.
Get rid of the if. Just do the trace as the first argument, and the second argument.
Oh, I see what you can do. Yeah. Okay.
Yeah.
Okay. Trace of that, comma, list
underscore, L underscore list goes to framed of L. And then from 0 to infinity. Yeah.
Okay, that's helpful.
There's some misfires though, I think.
What do you mean?
Like the second argument of the do. Or no, sorry, never mind.
Oh, yeah, I mean, that's correctly a list, although it's a list of a different origin.
Yeah.
Because we're basically reusing list here.
Yeah.
Avery points out that there's a resource function called trace sprint evaluations. That I'd forgotten trace sprint. What? Oh my gosh, what is this? This stuff is all so obscure. We have got to demystify all this stuff. What does trace sprint? Go ahead.
Sorry, I think this type of example in which we have a function which is recursive is a better example because you see the reevaluation.
Okay, all right.
So just let's copy this definition and do trace of something here.
I just have to remember to use a kill off my session after I've defined all the single letter names. Okay, so now you say, let's do the same deal here, just so we can see where everything is, of trace of
f of 4 or something. Okay.
Oh my gosh, what are we seeing here?
So f of 4 is replaced with f of 4 minus 1 plus f of 4 minus 2.
This part I understand, yeah.
Actually, so then it has to go inside and evaluate each of them. So it opens a new level of list and it evaluates f of 4 minus 1 and f of 4 minus 2, which get combined at the very end. You see the 2 plus 1, comma 3.
Yep.
Okay, but if I say trace f of 4, comma f, I'll see only the f evaluations. And that thing that I'm seeing here will have the structure of a tree. Is that correct? So if this is a Fibonacci tree, is it not? Can I make that into an actual tree somehow?
I will add a structure to expression tree for it. You'd have to use nest tree. Do it yourself.
Okay, but
actually, I'll try to come up with an example real quick.
Okay.
Perhaps expression tree of sub-expressions?
There's no autocomplete, by the way, here. I'm complaining about autocomplete. Maybe Avery can make a note of that.
Oh, again, the whole forms. Yeah, you complicate the thing. Yeah.
Right.
So we need a special type to eliminate all the whole form stuff.
Maybe we need a held sub-expressions for expression tree.
There is a held sub-expressions, but it's still going to have all those hold forms in there.
I see. And by the way, your printing should not have the printing of the explicit hold forms in it.
I mean, that's just the symbol hold form.
Oh gosh. Okay, all right, okay. But anyway, let's look at this here. So this is now a Fibonacci tree, but how do I see? And you're saying that everything in the sequence here is what I'm calling my God, this is confusing. I am so confused by all this stuff. Okay, if we take this and we say trace of that, what is going on here? You're saying this sequence, where is my kind of time-like evaluation sequence?
So time-like is like f of 4 minus 1 is that next box that you see with the whole f of 3, all of that.
I see.
That's everything involved in computing f of 4 minus 1. And then the next one's everything involved in computing f of 4 minus 2.
Question for physics project people. what is the relationship of these relations and causal graphs and causal relations? It seems like we've got our, I'm quite confused here, but is there some obvious way in which there is a, okay, could we draw this as a graph? First question. Could this naturally be drawn as a graph? Because, when we built Trace in version 2 timeframe, we were, it was long before we had graphs. So were we to do this today, would we end up with something more like this graph to represent what's going on? What is the evaluation graph, basically, is my question. And it seems like what seems like what we have here. Okay, can somebody see what would be the natural? I mean, the natural evaluation graph here, I think I drew some recently, is just this Fibonacci, is more or less a Fibonacci tree in this case. Everybody's silent. Is that because everybody's confused, or
can I make a comment?
Yeah, please.
Yeah, so at least from my vantage point, it seems like the obvious way to represent this, as a poset or something, is to say this, this nesting is, those correspond to the actual time-like edges in some Hasse diagram, right?
Mm-hmm.
And the locations where individual rules get applied, which, in the fine equational proof, case is just literally a part specification. Those are then split up into individual sub-expressions that lie on, potentially on one antichain.
Okay, right. Let's unparse this for a second, or parse this somehow. What you're distinguishing here, you're describing it as a poset, which is of course correct. So there are, okay, first point, there are things on antichains. There are things that can be evaluated simultaneously. Well, in principle, I mean, if I say something like 1 + 1, 2 + 2, 1 + 1 and 2 + 2 live on an antichain because they are in principle separately evaluable. Do we agree? I mean, that's the kind of thing you mean, is that right?
Right. But the point is that the thing that you're referring to as, space-like separation or something, which, is in fine equational proof is just literally the part expression, the part specification of what sub-expression had a transformation applied to it. Those, if those sub-expressions don't overlap, then kind of by definition, it doesn't matter what order you evaluate them in, right?
Yes.
So there's a natural representation of this thing as a partially ordered set where each individual non-overlapping sub-expression is treated as a separate element of the antichain, and that the actual order structure is showing you the recursion, the time-like recursion depth, the nesting.
Okay, but hold on. The very fact, look, there's one question. Given a piece of code, and this is a question that we're interested in for other reasons, given a piece of code, can it be evaluated in a multi-threaded fashion where different things are happening on different threads independent of each other? And that is essentially the anti-chain question, is it not?
Right. And so like if you take something like this, you've got, in this case, the individual sub-expressions to which, in this case, combinator reductions are being applied are literally represented as antichains.
Okay, now we have to understand this.
This may not be the ideal example. It's just something to indicate what I mean.
Okay. All right. So let's do people understand? Okay. Just to make sure everybody's on the same page in terms of what we're talking about here. So among our objectives is to be able to understand. So a sub-objective, what can in principle be evaluated on a parallel thread in parallel, aka what is on an anti-chain in the quotes evaluation post set. Is it an evaluation post set? In other words, what I'm confused by is the spatial aspect of evaluation. That is the different parts of expressions. Is this, I think, okay, that's my question. Is it the case that,
so coming back to the expression you just have there, this trace. So for example, we have the F4, and the F4 happens to evaluate to a sum of two things. So now you have to evaluate those two things separately. And that's why you have now two lists following, each one evaluating one of them. So I think those are your threads. Your space.
Yes, that's correct. Those two things can be two separate threads.
Right.
Although it wouldn't be, in this particular case, confusingly, because of shared common subexpressions, it would actually be a mistake to evaluate those. Well, I don't know if it's a mistake. It would be that there is a fast way to evaluate this that does breadth first traversal rather than evaluating all the way down to the leaves separately on each thread. That's a confusing case. Does that make sense? I mean, in other words, Fibonacci, if I were to go another level here and say, f of 5, this is the classic case where breadth first evaluation is useful. F of 5 goes to this goes to this, and that then goes to, f of 4 plus f of 3 plus f of 3 plus f of 2. And now, of course, if we're doing it breadth first, we can combine those two together. And so we no longer have an exponential number of terms, right? But we don't get to do that if we're splitting it in this evaluation graph. So this is part of, dagification, so to speak.
But I think Trace is being faithful to what's happening. If we had defined the function f with memoization,
I know. Yeah, I know. It's being faithful to our evaluation traversal order. Yes, it is. Trace is a single way system. Trace is not showing us the sort of, there is a multi-way version of this that can be, well, let's see, that can be traversed differently, but that's not what this is showing us. But anyway, keep going. You would say, I agree with you that every box here can be evaluated on a separate thread.
Right. So I think the time sequence is the horizontal thing, and then the spatial bifurcation is what triggers the nesting of nest things.
Yes, I think that's right. Now, just for some additional context, maybe somebody, I mean, at least they have the right note. Let's see, Richard posted something about trace functions in boy. Okay. And there's also another thing that we're certainly aware of called tracelets, which I think might be related, which I'm sure Jonathan knows about at least, which I don't know about, but they seem to have a good name at least. Let's see. Okay. There's
also a highly related notion of lenses in functional programming that may be worth.
What are those? I don't know what those are. Okay, but so we've got tracelets, we've got lenses, and now we've got Glocal multi-way systems. And we've meanwhile got the general question of what is a graph? What is the evaluation graph? How do we represent, and, in a sense, this is the evaluation graph of the proof function of find equational proof. Is that a true statement?
Well, no. I mean, and this is the point that I'm trying to make about Glocal multi-way systems.
Okay.
So if you take something like this, say, it's pretty obvious that substitution lemma 1 and substitution lemma 2 lie on an antichain.
Okay, so here's a proof, and now let's see. So I should take proof data set. or what?
Or proof graph or whatever. I mean,
Proof graph. Okay. All right. Okay. Well, I can't tell what those lemmas are. But let's show the
you can just hover over them.
I did. I know I can hover over them, but then I hover over one and then I hover over the other and I can't see them both together. Okay. So substitution lemma 1. What? I'm so confused.
This is the simplest non-trivial case of something like this, right? Where you've just got an expression of commutativity, and then you've got a function which is nested to recursion depth 2. So there are
yes.
So within that sub-expression, there are two places you could apply on the first level, and there's one place you can apply it on the outer level.
Yes.
And the point is, substitution lemma 1 and substitution lemma 2 have non-overlapping part specifications, so their order is.
I see, because they're applying themselves to
non-overlapping sub-expressions. They have non-overlapping part specifications, but that information is not encoded in the structure of the proof graph. Whereas if you were to construct a Glocal multi-way representation of it, as one can do, for instance, for a combinator calculus, then it becomes obvious that when that's happening, because every state vertex here is a sub-expression, and the causal relations express precisely when those sub-expressions are shared and when they're not.
All right, so let's go Glocal here. What should we try? Which example should we try?
I mean, the first is simple. It's just a fixed point combinator, but it probably illustrates what needs to be illustrated.
Okay. Okay. That's because we defined F. I thought that was going to happen to us. Okay. Oh my. All right, let's try to understand this. What the heck is going on here? Okay.
This is compressed because token deduplication is enabled by default. But so all that's saying is that, the event on the left there, which takes in y of f and outputs y of f, y of f, is ingesting 2 tokens of the form y and 1 token of the form f, and outputting whatever it is, 3 tokens of the form y and 2 tokens of the form f. And each one of those arrows is tagged with part specification information, just like it is in fine equational proof. And so then looking to see whether there are overlapping sub-expressions or not is how we determine whether there are causal relations or not.
Okay, for people who are not as familiar looking at this, let me try explaining this. Okay, so this is an event. The event is like a function that has certain inputs. In this case, it has 2 y tokens and an f token that happen to be arranged in this tree structure. And then there is a rule coming from outside this universe here, so to speak, that is what defines this event. And it produces this thing, which is y of f of y of f, which then, whose elements, there are 3 y's there, and they get used in this token y here, because there isn't token deduplication is not on. If token deduplication was on, this would be more DAG-like, and that y there would be the same as that y there. Is that correct? Jonathan, is that right?
Right, exactly. So there are multiple levels of token deduplication, but yeah, in effect, if it were maximally deduplicated,
there would only be 1 y in the system.
Right, exactly. So you could see that if you switch the option deduplicate tokens to true, you'll see that.
I have a very bad feeling this picture is going to become even more obscure.
They're very hard to read when they're deduplicated.
Now, the deduplicated version is very similar to a Petri net. Is that a true statement?
Yes. So in fact, it's for the graph rewriting case, it's precisely one reproduces precisely the execution semantics of a Petri net for typed graphs.
Okay. So I just we have multiple people here who have different expertise. Like, for example, I'm going to pick on somebody like Roger. Are you understanding at all what the heck we're talking about here?
No, sorry, I was answering an email right now. So no, not this one.
Okay, I think this is relevant to you since you understand Petri nets and things.
Right.
Okay, let's. Well, okay, but the point here, what we're trying to discuss is what is an evaluation graph for our language. Okay, what is it? What is the best representation of the evaluation process as a graph? Okay, and the representations we have so far are the trace representation, which loses tons of information, because in particular, the trace representation doesn't tell us, it tells us what the output of every transformation is, but it doesn't tell us how the transformation was made. Right? It doesn't give bindings for the pattern variables. It doesn't give positions where replacements were made. It doesn't give any of that information.
So when you teach it, you have to give a model to the user, right? So a classical model is the substitution model of evaluation. And that is equivalent to basically an animated graph, a graph that sort of changes over time, right? You know, and
no, it's no, that's completely unobvious to me. That's completely unobvious because remember, one of the key things is
so you let's say that you have f of x comma y and you substitute in an expression for x. Now that x becomes a sort of a tree, you know, like in itself, a little graph.
Okay, so what you're proposing there, what you're saying, which I mean, I think I believe that's an obscure way to think about it, but we can go down this route for a second, okay? In fact, we've never made these pictures, even for combinators, of clearly with combinators, as you evaluate the combinator tree, you will get, maybe we could trivially make this with Ian's tree stuff.
But what I was going to say, you had, at some point earlier, you showed a case where each node was itself a graph. And so there's nothing that says that you couldn't put that animated graph into a giant super graph where all the nodes are graphs.
Sure. No, that's exactly what, I mean, that's what we're doing. For example, when we make these multi-way graphs of graph rewriting systems, that's the global multi-way graph. Jonathan has these Glocal ones. We also have local multi-way systems where what's happening is you are, the problem with a global multi-way system like that is there's lots of redundancy because you have the whole graph and you show a new state of the whole graph, but actually only a tiny piece of the graph changed.
Right.
So you're making a copy. I mean, it's like saying, it's like doing a replace on a giant expression, but only one piece of the expression is being replaced, but yet you're showing the whole expression again. Now, in implementationally, it is not so expensive because it is very daggified. You know, there are common pointers and things there, but serialized in the language, it is extremely long.
Yeah.
Right. So, I mean, the thing we're trying to do, and the thing that I think is super difficult, is the trade-off between you have an object that you can pick up and hold and so on. That is a global thing where you have a lot of redundancy, versus the thing has been smashed into pieces. Every piece is unique, but you don't know how the pieces go together again. Is that I mean, Jonathan, others, I mean, is that a reasonable characterization of kind of the trade-off here?
I think so, but can I make one comment in relation to why I think the local/glocal approach, why I think there's merit in seriously considering that if we're talking about theorem proving in particular, although I suspect it applies more generally to evaluation in the language.
Okay,
go ahead. Very often you want to form lemmas based on sub-expressions, not based on expressions. Right. So right now, when we use a previous lemma or an axiom or something as a construct to produce some rule, we use the whole object, right? We use the whole construct.
Yes.
But you can imagine, you can imagine having a situation where, so, suppose you're doing theorem proving over, I don't know, Boolean algebra or something using the NAND operator, and you've got two very big, complicated, highly nested NAND expressions, which are identical in all of the outer packaging, but deep nested inside, there's an A NAND B, and on the other side, there's a B NAND A. So the proof of that expression has implicitly proved the commutativity of NAND, but to know that, you'd have to, peel back all these layers of packaging and find the thing that's nested deep inside. So the find equational proof, which is in a sense based on a global multi-way paradigm, wouldn't be able to infer commutativity just based on having proved that lemma, whereas a theorem prover based on local or Glocal evaluation would.
So you're claiming that find equational proof as it is right now would, if it had, is that in fact something that happens in for example, the proof of my axiom? And I mean, do you know whether that occurs? That's an interesting case. Where, I mean, do we know whether that happens? I mean, interesting.
Well, obviously not for commutativity, but there are certainly cases where where two expressions are proved to be equivalent, where they differ only at the level of one sub-expression. That occurs quite frequently in proofs that involve,
Well, let's be specific here. Okay, so let's say okay, so let's just pick up a bundle of how can we get this? A bundle of actual relations here. Let's do the NAND operation but commutativity, for example. So let's say find equational proof of P center dot Q equals Q center dot P with that. Okay, so now, Jonathan, how do we get out the actual series of equalities? And this is, by the way, another thing that is an issue is sort of the extraction of pieces. What is we have to dig into this data set. So is it statement? What do? We say all comma statement?
Yes, within the data set, yes.
Right, so proof data set, all comma statement. Okay, so now let's say values of that. Okay, so now this, and now we're about to use Ian's, let's do normal of that. Okay, oh my God. Ugh. Look at this creature. Actually, it's not as bad as I might have thought. It's not as bad as I might have thought. Okay, so now can we make trees out of these? And can we? Yeah, but I mean, I think what we want to do. So the case that Jonathan was talking about is there are two trees here, which are very similar, whose outer levels are the same. So what we want to do here, I think, is to say, and I would really like to do an expression tree where I don't display any variables and things. Can I do that?
To say tree element label goes to all, goes to none.
Okay, so expression tree of that, tree element label of all goes to none. Is that right?
Yep.
Like this? Do I need the parens?
Nope.
Okay. And then I want to do this mapped at level 2. Is that right? Why is it taking so long? Oh. Okay. So there are all of our equations. Okay. It's kind of interesting that so many of them have that same left-hand side. By the way, already, this helps me in understanding a bit what the heck is going on. Maybe it helps me. I don't know if it really helps me, but because we're looking for other kind of proof representations. Okay, so the claim, okay, so now how would we tell which of these have the same outer levels of that tree? Obviously, they're a variable. I mean, so for example, if we look just at the non-terminal structure of these things. Like that one obviously has a top level that's the same for what it's worth. Is this, I mean, Jonathan, is this what you had in mind? I mean, we're asking, are there pieces where, I mean, and this is somehow what the heck is it? It's
right. So exactly. And so the point that I'm making is that with say a Glocal multi-way evolution, you can trace the you can trace the evaluation history of an individual sub-expression rather than the whole expression. Right. And so you can do lemma formation with a much higher granularity.
Yeah. Okay, but I mean, so our evaluator, what does it do in terms of that? I think it does that too, because it's going into sub-expressions to evaluate them. It doesn't take the whole thing in a big gulp and do something with it. It goes into the sub-expressions to try and make transformations on them. So okay, so maybe in the Glocal multi-way system here, one of the things that you're doing, so you've got the tokens, you're recording what tokens get produced in these computations, but you're not recording at this level. I've just got a bunch of Y's and a bunch of F's in a bag. You're not recording the structure that those live in.
So each of those edges is invisibly tagged with essentially a coordinate for what level of the expression tree does that particular token lie at. And those part specifications are then what are used to determine causal relations between the events.
But so this F, that edge says this is the 2-to-1 part of the expression is going to be that F.
Right.
Now that F is used again, how the heck does it even know? I mean, it has to reconstruct itself to be able to know where it appears in this event, doesn't it?
Yeah.
Which is, so that's again the trade-off between, in a global multi-way system, you've got the whole expression structure there and you're operating on it, you know where everything goes. In this case, it's been shattered and deduplicated to some extent, but you don't know where everything goes, so to speak. But what you're saying is these causal edges, okay, these causal edges are saying that there is a thing here that will be used again here. So do you have, so these ones out here are causally, I'm fairly confused here. You're saying that these different causal edges represent different independent parts of that tree being consumed in subsequent events. Is that right?
Right.
So in a sense, wherever there is a causal edge, it is defining a time-like relation, which is defining something which cannot be on an anti-chain and therefore cannot be done separately in parallel on different threads.
Right, exactly. And that's the thing which I claim is, again, I can't speak to the internal details of the evaluator, but at least find equational proof does not out of the box support making that distinction. You can infer it from the part specifications of individual lemmas, but the proof graph itself doesn't contain that information.
Right. So what you're saying is
the stuff there's a label there. Is that some kind of synchronization event?
You can think of it that way, yes. Because what that's doing is it's having to collect
the results or something like that.
Yeah, it has to collect the results so far and do them. So for instance, these two things are completely independent. Yes, I think you can think of this as a synchronization event. Anybody else want to comment on that? Because it's got to collect all the pieces that go into it and then do its thing. And unless all those pieces have been correctly assembled, it can't run. So it's kind of like a wait type thing. We should have had Roman in here as well, because this is now his kind of world.
But that's also Petri nets, where they basically, those are the preconditions to be able to do the next transition.
Yes, but as we were saying here, when you were not paying attention, Roger,
I am paying attention.
If you deduplicate all of these tokens, in other words, now I'm even more confused. I would have expected, okay, so if you deduplicate all instances of Y, I thought, that corresponds precisely to a Petri net here. But why are there two Ys here?
Because they exist on at different moments of time.
But is that still in the Petri net formalism? It's still this, or do you have to deduplicate all the way to get to true? Don't you have to deduplicate all the way?
You would have to if you wanted to get a true Petri net, yes. So okay. Each token becomes essentially becomes a token, and each event becomes a transition firing.
Right. So Roger, that's the relationship between these things.
Okay. Well, then I'm at least in the ballpark.
What's that?
Then I'm at least in the ballpark of that language that you guys use.
Right. Okay. But so the thing we want, again, repeating, the thing we're trying to get to is a reasonable representation of the evaluation process as a graph where we can see causal relationships between different we can think of the evaluator as taking a series of actions. Some of those actions are events. Some of those events are causally connected to others, and some are not. For example, in the list, 1 + 1, 2 + 2, the evaluation of 1 + 1 is not causally connected to the evaluation of 2 + 2. But if that whole list is then going to be ingested later, you better have evaluated both of those things before you get to the next ingestion point, before the whole list is ingested. So trace is one corner of this.
And I think you guys had it there, but I think it's going to be crucial to not go too low level. I mean, or sort of be able to specify what level you want tracing or graphing to sort of happen.
Oh yeah, sure. Yeah,
because there's a lot of, for all kinds of practical reasons and theoretical reasons.
Well, trace has a not totally terrible interface for that. I mean,
yeah,
trace allows you to do a pattern.
It's clearly sort of some thought of that.
Right. But I mean, and that may be sufficient to say, don't break, only show us things correspond to these patterns. Now, of course, that might be incomplete for the graph. That is, just looking at what happens to those patterns might not explain what's going on, if you understand what I'm saying.
Right.
Like evaluating Fibonacci, it might do fine, but if there was an additional twiddle where you did some, secondary, GCD computation, you wouldn't see that. It would just be an oracle, so to speak, of delivering the result.
Yeah. But then you can kind of drill down basically at that level, right?
Right. So the claim would be it is explicit things. Yes. Okay. Fair enough. And then there are oracle deliveries of things where it's not explaining why that happens. It is just something that appears through some mega event or something.
Right.
I'm a little okay. But the mega event. The point about our evaluator is that mega event must get its input from something in the evaluation graph.
Yeah, but I think that's super useful for all of these things we're talking about, like parallelism. What is the granularity of parallelism? Or I'm using functions that someone else wrote. There's supply chain. Someone wrote it. I can't really drill into them.
Fair enough.
But I know it's wrong, and I pinpointed that's wrong.
Okay, but I think it's useful comments that the granularity of parallelism is the same story as, okay, in most of what
debugging at different levels of abstraction is also kind of useful.
Right, but in the physics project, unlike the metamathematics project, by the way, but in the physics project, we don't have a lot of hierarchy. That is.
But didn't you have it in the mathematics? Didn't Jonathan talk about sort of lemmas or something like that? Lemmas and lemma. This is all expanded or it's all contracted type thing. That's kind of hierarchy.
Maybe. Maybe
you call it something else, but I think
well, there's a yet different thing in studying this MetaMath database. They have this notion of definitions, and their notion of definitions really does capture. I mean, that is yet a different form of hierarchy. I can probably show you. I'm not sure if I should open this file because it may be. Let me see.
But lemma is like an abstraction, right? I don't need to see how you prove the lemma, and I'm just using it.
There are multiple different kinds of abstractions.
Sure.
A lemma is more like a caching of a bunch of.
Okay, if you use it like that, yes, then I agree. That is more like caching. It's in the same tree, but I want to reuse the state. Yeah.
Right. Let's see if I can open this. Even open.
But so what I'm saying then is it's like a bigger axiom system, I guess, in that context, like a much bigger axiom system.
Yes, I mean, so I'm just going to show one thing here if I can find it. Let me see. Looking for something here. Let's see if I can pull it up. Oh,
a more efficient axiom system.
Right. So here we go. I've got one. All right. This is from this MetaMath system, which not to be confused with metamathematics. This is a definition hierarchy. Okay. It's defining plus ultimately in terms of the operations of set theory.
I see. Interesting.
Okay, so I think I have one for, yeah, here's one for GCD. So it's like, what do you have to know about? I mean, it's kind of surprising you have to know about reals here in defining GCD, and maybe the definition isn't right. But in the end, you're going down to the pure operations of set theory. And you have a more and more complicated, as you go higher up here, you're able to package in more and more.
But the question is, like, wouldn't surprise me if there's an intermediary level that you could, I mean, I can even see it in this graph where you don't drill below, and I could say, well, just use these as a base, and I got myself a plus.
Yeah, exactly. Right. No, but as I say, I think this is an orthogonal issue to the issue of lemmas. I think definitions are an orthogonal issue to lemmas, I think.
Well, they're not entirely orthogonal, right? I mean, they're in a sense, they're just lemmas that you bake in at the beginning rather than that are generated on the fly.
Fair enough. Fair enough. But they also define terms. They define new terms and things.
Right, but the point is, each one of those operators, if you write this in terms of some predicate calculus or something, each one of those operators is just going to be ultimately some quantified equation that says this composition of expressions equals this other composition of expressions with different kinds of operators on the left and right.
Yes. Okay, but let's come back. Okay, do other people have comments here? Nick, do you have any comments? Or
well, I can say that the definitions can also be think of as disambiguous theorems, because when you don't have to guide it how to prove it, you can just parse it to get its proof.
I see. It doesn't have there's no proof chain around it. It is merely a syntactic statement of this thing being defined. It's like a macro of some kind. Is that right?
Oh yeah, it's like how you start parsing. You usually only have like one correct way of arriving at the correct AST, abstract syntax tree, right? Well, if you're given a theorem statement, could be many proofs of how can I arrive at it, right?
Right, but you're claiming this is a rather simple-minded macro language that has an unambiguous parsing and so on.
Yeah, like MetaMath is.
Yeah, right.
I mean, as I understood it, with theorems, say in an entailment cone, I mean, you're going to get there via entailment, but with a definition, it's a different kind. I mean, it's being constructed with at a different level in our framework. This is kind of, it's at the EAM level.
This is such a bizarre and unfair conversation because we keep on using these terms that come out of this project that are absolutely incomprehensible to many people. Anyway, okay, yeah, but go ahead. At least I understand, I think, what you're talking about.
Well, the point is that you have to have this tree, you have to have this parsing computation to use the definition. Once you have your definitions, at least in the way that the MetaMath language is set up, once you have those, then you can get something like the kind of entailment cones that we have. But it's a kind of it's a computation you have to do beforehand, before you start to have actual entailment structures or entailment fabrics. That's how I view it, at least. Nick?
Right.
Yeah. Right. Yeah.
Okay, so let's see. So let's come back. I mean, again, gosh, where to go from here?
By the way, Stephen, can I just clarify something in relation to trace?
Yeah.
So the example you gave before was the example where you have a computation that bifurcates into, where an evaluation bifurcates into 1 + 1 and 2 + 1.
Mm-hmm.
Or 2 + 2, sorry. But what I was going to say was, isn't the more relevant case where it bifurcates into 1 + 1 and 2 + 1, where, say, the right-hand one on each side is a sub-expression that came from a common previous evaluation?
You're saying that will be the case where they are causally connected?
Right.
Probably. Can you see how to make an example? Because I was having a hard time, forming. Let's see. But okay. Let's review our objectives. One objective is to have a better graph representation. Okay, the graph representation of find equational proof says we're basically taking a rule and applying it. In the case of find equational proof, we're applying it to a rule effectively, or we're applying an equation to an equation. The more general case is that we're applying a transformation to an expression. And so we can view every step in the evaluator, we can view as apply a transformation to an expression. And that transformation might be some built-in transformation deep in the internal code of the kernel, or it might be something that we can explicitly see. Is that a fair statement? And so then every
plus side effects.
What's that?
Plus side effects.
Yeah, side effects are ugly. Okay, so the summary here is kind of like operation of the evaluator is each step, oops, why is it beeping at me? Each step, takes an expression, a sub-expression, and a transformation, which might be an explicit, rule from a colon equals, or it might be inside the kernel, which might also be implemented as a rule, whatever. Okay, and then it returns, then each step returns a new sub-expression. And then we have the meta, then the extra piece is sort of the motivator, the thing that's doing traversal orders. The extra piece is, where do you go next? AKA traversal order. And that could be, if we were able to execute in parallel, that could be we do multiple things next. Do we think that's a reasonable summary of the, meta summary of the evaluator? comments from people? Christopher, anybody?
Well, there's also attributes.
Yeah, but that's partly where do you go next? Somewhat controlled by attributes. And what we're not, okay, so another piece, changing the symbol table, aka shared pieces, aka DAG-like behavior, I think. But so,
well, you don't really see the DAG-like behavior. I mean, I think the main thing with the symbol table is just that's where side effects happen.
Right. Right. I mean, we were just talking about, actually, in a different discussion on the subject of DAGs, we were talking about a different topic, but it's related to this, infinite data structures. And in which, that's the x equals x plus 1 data structure, or the x equals list xx, where the claim is that instead of those being expression trees, they are expression DAGs. Maybe they're not even DAGs. Are they just graphs?
No, they're graphs. That's why they're a problem.
I'm so confused.
Expression DAGs, I think, are no problem because those aren't infinite. Expression graphs are where you get infinite expressions.
Right. I mean, isn't it interesting that we have?
Do you mean that expression x equal list?
No, I mean the result, the thing that is produced.
Okay.
I mean,
you mean like an infinite expression that is a list of itself twice.
Right. Now, Nick has some technology for this. Could you maybe put that? I've already lost the.
I mean, you can view this as equation solving, and the only solution to those equations are these infinite expressions. Do you know what I'm saying? The fixed point, if you're using Dana Scott's terminology, is basically these infinite expressions.
Yes. Is that Dana's terminology? Did Dana that anyway? Who knows?
That's his denotational semantics business.
Well, I know that, but I didn't think he. Anyway, we could ask him. But Nick, were you going to put that? Could you put that in the chat or something? The link to your. There we go. Okay, thank you. So this is, I guess, a somewhat toy thing from Nick of infinite data structures. Can you explain?
Well, yeah, it's just based on one constructor that has a hold argument. And I just defined a bunch of functions for a regular list that work on a lazy list, like map select, like joint, even parallel map with partition.
Okay, so what is this? So this is a representation. So if I say length of this, what will happen? Splatteroo. Okay. So if I say take 1s, 5. Okay, it didn't happen to work, but that might have worked.
So
is that a true
you
statement?
can ask normal of it.
Of this?
Do not, yeah.
Oh, because it didn't. So that's another issue for these infinite things. To what extent does it auto-evaluate? Does it auto-resolve? Because clearly it can't infinitely auto-evaluate. Right? So for an infinite expression, how much auto-evaluation is possible? And what you're saying is you're just asking for normal when you know it's going to be whatever. So you have. Okay,
you can apply like lazy eval 5 to a lazy list, and it gonna evaluate 5 times.
Okay, so lazy eval of take 1s, 10, let's say, and I'm going to do that 5 times. Oh, that's cool. Okay, so can I try this with if I do this data structure here, will it work, or is it hopeless?
Like what? Yeah, you can make a tree too. Like if you have a children of a tree, it's gonna be an infinite list, always a list. You can make this.
Sorry, how do you do that? Okay, so this one here, you've got Fibonacci, and so this is an infinite Fibonacci tree. Is that right?
List. It's a list.
How do I get the? This is a list of
Fibonacci numbers. The only like thing here, like, do you just want x equals? Do you just want, what is it? X equals cons of x.
Technically, I have a lazy tree already. I just not tested it properly.
Yeah.
You can.
It's funny. I have a notebook that's almost exactly the same. I mean, this is a classic like Lisp Haskell thing.
Yeah.
The main issue I ran into though is the fact that it always has to it unlazily computes the first element. So sometimes there are some things you can give it where it might take it a long time to produce the first element. But yeah.
Is this the okay, yeah, this is the project you worked on with Luis, Jonathan. So does this, what did you guys do here? So what?
So the main thing, it was Luis implemented sort of lazy list evaluation of the standard kind. The place where it gets interesting is then we essentially defined a sort of algebra on infinite lists. So when you've got a generating function, understanding how those generating functions compose under things like unions, intersections, joins, etc., proving that lists are equivalent. These all turn out to be actually quite subtle problems of automated theorem proving.
Well, essentially what you're doing is you're describing a list by its generator function, and then you can describe a list by its generator. Yeah, in fact, this is the classic reason why one introduces theorem proving in mathematics, in a sense, is you describe a list by its generator, and then can you e.g. prove two lists are equivalent?
Right. And so we had sort of toy examples where we could do that, or where you could prove, for instance, that if you joined two infinite lists together, you'd get a different, you get something that's equivalent to some different infinite list.
Right, but I mean, proving two lists are equivalent is basically proving that two expressions are equivalent, which is sort of the classic problem of find equational proof, for example. That given you're asking, given the evaluation semantics, are these two things ultimately equivalent? Like, do they have the same fixed point? Do these two differently stated generating functions have the same fixed point? If I'm not mistaken.
Right. But there's also even without doing list equivalence, there's still a use for kind of ATP, or at least automated expression simplification, just in terms of doing algebraic operations on lists.
No doubt. Yeah.
If you take two arbitrary generating functions and you do a join or a select or cases or something on them, then you're going to get some much more horrible composite generating function, but in a large class that can be simplified.
Right. I mean, Roger, that is very analogous to things that we have to do. And I mean, if you have an algebraic function and it describes a solution set, and then you have another, you have something which describes the integers, for example. Okay, you have two equations, and isn't this very similar to what we have to do in algebraic equation simplification?
When you say generating functions, do you mean generating functions, or do you mean something special to lazy construction?
Not generating functions in the mathematical sense, just literally a thing that takes in a list index and outputs an element.
Okay. Right.
So what I'm saying, go ahead. Yes, I mean so it's a little different.
But the thing is that we kind of carefully, we don't entirely, we can't avoid sort of undecidability, but we avoid a lot of it.
Right, it's the same issue here. Can you take two things with symbolic representations for these infinite structures and combine them?
Mm-hmm. And for some things, we have many of these. We have quite a few of these sort of representations, like different holonomic functions, differential roots.
Okay, so go ahead.
They give you sort of an implicit form of generating something infinite, meaning that you know an infinite power series for it, meaning you know an infinite precision evaluation for it. Same with roots, they're implicit, but you can evaluate to your heart's content as far out as you want.
Indeed. So you see this thing with these lazy infinite structures, somehow that reminds me of traversal orders in evaluation, which reminds me of the thing you were saying, Roger, about, how far down do you go into the weeds, so to speak.
But by the way, with the cons list things, I mean, that's sort of exactly traversal order, because again, the whole point is just that, I mean, this cons here is there's nothing special about it. It's just a symbol with the attribute hold rest.
Right.
And so in what sense does that define traversal order?
Well, I mean, basically you're telling it to
what to do next.
Yeah, you're telling it not to traverse down the right-hand side, because you'll get lost forever. I mean, instead you just, you do the left-hand side, and then yeah.
I think we're hearing lots of weird background noise, but unfortunately we're quite over time, and I realized that we had Jeremy here because we were going to talk about the graphical appearance of automated find equational proof output, which we have not managed to do, because we're in the end we're going to have, I think, a master appearance for the I think this is going to be the same as an evaluation graph, because I think it's going to be unless I'm totally confused, this will be the evaluation graph for the proof function. Is that true, or am I confused here? Anybody have an opinion about that? Jonathan, do you have an opinion about that?
Close.
Yeah, I think.
Yeah.
So, I mean, go ahead.
Modulo the usual subtleties that we kind of discussed yesterday.
Yes, but I mean, yes. And I mean, this question about there are variables being defined, and those are in your proof function right now. What does your proof function look like right now? Your proof function, for example.
For instance, only checks substitution lemmas. As Jose was mentioning yesterday, it doesn't. We never found a nice representation for critical pair lemmas, although such a thing exists. I just never got around to implementing it.
But so wait a minute. So what you're saying is the substitution lemma is a straightforward replace at. Is that correct?
Yes. Yeah. Or internally we implement it as a map at of replace.
Yeah, that's what I meant. There isn't a replace at. Yeah. Okay. So that's a substitution lemma. Go ahead.
Though arguably there should be.
Yes. Arguably there should be.
Replace at was approved in ILD, or am I misremembering?
I think it was. I'm okay. If it wasn't, Avery can go chase that and see whether. So critical pairs, aka by substitution, aka whatever. That appears to be much more relevant when you are operating on patterns, which is again a thing we are not doing language-wise. We don't have a lot of, there are two types of things we don't have. We don't have things that operate, well, many types of things we don't have. We don't have things that operate on patterns. We don't have a lot of functions that operate on patterns, that eat patterns and produce other things. And I suspect that's what a critical pair lemma naturally does. I suspect naturally that and maybe Nick, can you comment on this? I mean, you now have a function that essentially is a critical pair lemma. Is that right?
Yeah, it's a by substitution on rules. That's my interpretation of it.
Right, but so whereas a substitution is a pure sort of structural substitution on something which might happen to be a rule, a by substitution is a specific kind of operation that operates on something which has pattern variables in it. It's not interesting unless it has pattern variables in it. The true statement?
Well, if there's no pattern variables, then it's just substitution. Because it completely mimics the substitution case also with some extra capabilities.
Okay. Yeah. Right. Okay. So
sorry, as I was trying to articulate yesterday, there is a very important subtlety, though, which is that unlike for substitutions, in a critical pair lemma, the input can be sort of generated ex nihilo, if that makes sense.
Sorry, say that again.
Well, so it means with ordinary substitutions, right? You've got an input, you apply a rule that's derived from some construct, you get an output, right? It's clear where the input comes from. It comes from somewhere else in the proof graph.
Mm-hmm.
With a critical pair lemma, that doesn't need to be the case. It often is, but it's not necessarily true.
No, it's like if you have two inputs to a critical pair lemma, that's all information you need in order to reconstruct the output.
Of course. But the point is the input doesn't need to have been an expression that was previously defined. It can just be an arbitrary expression. It doesn't need to have come from anywhere.
Sure. Just like in a substitution, the rule that's being applied could just be sprinkled in from nowhere. It doesn't have to, that rule
except the rule is derived from axioms. The point is the common sub-expression that appears in a critical pair lemma is the only thing in this entire proof graph that doesn't necessarily need to have come from anywhere. It just needs to exist abstractly.
That's a common sub-expression. It's a sub-expression of some of the inputs. It's always the case in the proof graph. I haven't seen an exception to that.
Jonathan, do you want to comment on that? That where Jonathan is saying a critical pair lemma could just be consider the random expression blah blah blah. Now notice that, but the thing is that the now notice that is a common sub-expression of these two things that are coming in. You're not going to have it's irrelevant, it's free floating unless there are a pair of things coming in to which this critical pair correspondence can be applied. Is that right?
Right, but the point is that I'm sorry, go on.
Well, yeah, it's like if you have two inputs, you have multiple ways to unify sub-expressions of those two inputs. And as soon as you pick the position where the unification will be happening, that's it. You can just make a by substitution, and that's the result of your critical pair lemma.
My question is, based on what Nick is saying, with by substitution or co-substitution as involving these sub-expressions, I don't see how that's ex nihilo, because you're still going to be working with whatever you had before. You're just working on sub-expressions of them as opposed to what you would do with substitution.
I think what Jonathan means is you could just say, consider this expression. But that expression, I claim, will be untethered unless it appears as a sub-expression of the things that are coming in. Or am I confused? Look, I mean, okay. Jonathan, any thoughts about that?
Well, yeah, so the point is that the operation by which you obtain the critical pair from the inputs of the rules that went in or the constructs that went in involves taking a context and then doing a matching using most general unifiers, all of which is not going to preserve the structure of the input. So you can end up with outputs that will then match some future pattern, which is why you produce the lemma in the first place. But the common sub-expression to which you applied the rules doesn't need to have come from anywhere previously.
I think I understand. I'm not sure I fully understand.
But isn't it going to be the left-hand side of your matching construct? It's like
it'll be derived from that. Yes, sure.
Yeah.
But the point is, there are many different ways that you could unify it.
Yeah, but that's the point of proof. You have to find a way. As soon as you're given a matching construct and a position where the unification happens, that's all the information you need.
No, I don't disagree with any of this. I'm merely making the point that in all other aspects of a proof graph, when you apply, a construct where one side is a pattern and the other side is not a pattern, the binding of the pattern terms to actual concrete expressions is already known. With a critical pair lemma, it's only known after the substitution's already been applied.
After unification.
After unification. Yeah.
Yes.
So you just have to repeat the unification.
I think you're probably saying the same thing, just in slightly different ways.
I think so too. I think
because Nick has this, he has this new substitution, co-substitution approach. But it sounds like, if I understand what Jonathan is saying and what Nick is saying, is you're basically doing it on sub-expressions. What Jonathan is saying is, yeah, but when you do that, you get something that you wouldn't have seen before had you not.
No, but you're not doing it on sub-expressions, James. You're doing it on sub-patterns. And then the output involves concrete expressions.
Right. That is the nature, which I finally more or less understood, of co-substitution, where you are instancing the operand rather than the operator, so to speak. I think we're getting into a deep rat hole here, but I do think that the meta point here is that there may be a bunch of natural operations, including some that Nick has been looking at recently, on pattern expressions that we've never had, because we've never really manipulated pattern expressions. Pattern expressions have always been the thing coming in that does stuff to something else, rather than expressions that we manipulate. So I suspect there's a project that needs to be done that is, functions for manipulating pattern expressions.
I think manipulating both patterns and functions. We've done this many times in the past, something that was kind of dead meat just for evaluation, like graphics primitives, and they become alive. You can manipulate them. You can do all kinds of things around them.
Right.
And, if it would be fun, then we can really do, maybe easier to do meta programming, generating functions basically from all kinds of functions.
Okay, so you're saying this is, functions that manipulate pure functions, basically.
Yeah. Would, create functions, generate functions, transform functions.
No, you're right. And then the other thing that we were just talking about in another discussion recently was functions
which obviously the compiler folks do one in very important aspects of, but I think it's broader than that.
Right. Like, for example, we don't even have a function that renames the dummy variables in functions. That's a very elementary thing, e.g., renaming / canonicalizing, dummy variables in nested functions. Now, that's analogous to like Jose's tensor manipulation, I think. What's the analogy between, boy, we're zipping around between so many different areas, but what's the analogy between a dummy index in a tensor and a bound variable in a function? They have to be very similar.
In the tensor, we worry only about two constructs, table and sum. Well, here this is more general.
Okay, fair point. But go ahead.
We found that we do some of this meta manipulation, but in a more kind of mathematical part of the system. So we have basically scoped variables, but they're not scoped in the core programming language sense of function. So Laplace transform has a first Laplace transform function of x comma s. That x is scoped.
Right.
See what I'm saying? It's not a free x.
Yep. Well, with integrate or something like that. Yes.
No, but it's sitting there. Like, let's say that you have an inactive Laplace transform. That x is scoped. It's not free.
I see. Mm-hmm.
Right.
And this question, if you have nested Laplace transforms, you can potentially be totally screwed because you've got conflicting x's.
Yeah. And early on, we found out that sort of some functions, and this is more to be done because there's a lot of theorems to be developed. But for instance, when you differentiated that thing with respect to x, it would literally differentiate it if it was a function of x.
Right. I mean, because we've got Laplace transform here, we can make it super confusing. We could do comma A comma C here. And then what the heck does that mean?
Yeah, we'll take that first thing and differentiate it with respect to A. That inner one.
Mm-hmm.
So,
well, differentiation is a very ugly, differentiation is kind of committing you to...
We fixed that, but the early version, I'm just saying that there are more of these things of interactions that's just like not right, not captured.
Well, I know, but this also relates to another big complicated thing that we've been talking about. What is a variable, formal variables, and so on? Because a formal variable, among other things, is a variable whose name has to have a definite name, but it doesn't matter what that name is.
Correct.
Which is, again, closely related to vertices in graphs, which have that same property. But you don't really care what the names of the vertices are for the purpose of thinking about it as a graph.
Right.
Well,
I think if just space, I think that it's actually very practical to be able to generate and to some extent transform functions, because that's you can generate code, you can do all kinds of things.
No, I agree. So this is look, we just had a good meeting a few weeks ago on held expressions. And I believe, does somebody remember what we generated? We generated a bunch of functions that we want for manipulating held expressions. And this is another case of, actually sort of a special case of that, is manipulating functions. And yet a different case is manipulating pattern expressions. It is funny.
There's a whole bunch of stuff, but by the way, there's a whole bunch of stuff. This is kind of a can of worms, but there's a whole bunch of stuff with like, there's a lot of automatic stuff that happens with, for example, if you have nested modules, or if you have modules inside of functions, or functions inside of modules, etc. When basically there are name collisions, or when you have a hold all function containing a module where it inserts its arguments into the module, and then the module variables get automatically renamed, etc., etc. There's a lot of stuff like this that we kind of do automatically, but where there's sort of, there are various kinds of nice programming language things you can, weird functional things you can do if that stuff didn't happen. Yes,
the fact that inserting into a function, or inserting into a module changes names is usually the right thing. But it feels like we need something analogous to splice, meaning don't change the name when we do the insertion.
Yeah, but there are several places this happens. It happens with module. It happens with function. Does it as well? If you have a function it doesn't even have to be hold all. It's if you have a function that takes another function as its argument. There's certain. Yeah, right. Whatever.
So we have here's an example of something that. So we have a function that's called discrete shift and discrete difference, or difference delta.
Mm-hmm.
And that's basically a substitution. If substitution knew about scoping, which it doesn't.
Right.
See what I'm saying? So
can somebody just give the minimal example for the name change in the functions? What happens here if I say function of a plus 1,
and then say comma for the third argument, just say hold all. That this will almost certainly work. But maybe in the function, hold on. I was thinking of an example of module actually. Maybe someone else knows an example of function.
But if I just do /.a goes to b, what will it do? Nothing much.
Well, if you put another function outside of that function, it will rename, with the variable a, it will, I think it will change one of them to $. I mean, it'll scope it correctly, but I mean, it'll change one of them to $. Try it. Oh, never mind.
Well, it turns it red.
Try say, okay, yeah. If you want just an example of one type of mangling, not just with function, you can do the thing with, if you have a hold all function containing a module and you insert something into that module, I think it mangles the module variables.
Right. Oh, Leonid wrote something about metaprogramming. Okay. Huh. Well, we should study this. Maybe ask Leonid about it. Seems like Leonid should be involved. Both Leonid and Roman are relevant to different aspects of what we're talking about here. All right, we should wrap up. Many different directions here, but I would say that these are definitely things to look at. And it seems like the elephant problem here is, can we make a evaluation graph for the language? And if we could do that, we could clean up trace. We could potentially have a nice way of having something where the fragments of that, where we could use that graph for find equational proof, and we would be able to take, and the real thing that would make that graph useful is that you could take fragments out of that graph and they would still be meaningful, I believe. Okay, actually, I've got a general comment about that. This is an interesting way to think about it. Okay, for one feature of any expression in a language is you can always take a sub-expression and you can still hold it in your hand, so to speak. It's still an expression. Every sub-expression is an expression. But for the evaluation graph, it is not obvious that every subgraph of the evaluation graph is an evaluation graph. Is it? Maybe there's a way to formulate it so that it is.
I think if you think of it as a partial order thing, then you can't take any subgraph because that's too arbitrary, probably.
Okay.
It has to hang together in some way.
I know, but that's the point. So every sub-expression is still an expression.
But the sub-expression is like a subtree, and if they're DAG, it's a sub-DAG, basically.
I know. Yeah, right.
So that's probably the analog.
Well, but I mean, see, because that would allow one. I mean, this is okay. So long ago, I had this idea that actually Bruce Smith was much involved with also, which was, could you represent a looping program and so on just by giving it's kind of like the analog of visual programming, but with greater generality, where you could say, here is this representation of an execution history of a program represented as a graph. Now I can just put it together with other graphs, and that defines as a symbolic thing execution history, instead of having a loop where program counters are changing, if that makes sense.
It's kind of like how net graph works, but you can't really have loops, I don't think.
Yes, it is. It's like how a visual programming, it would be the ultimate sort of visual programming story. If one could take an evaluation graph and fit it together kind of Lego style, that would be like a visual programming system.
Yes.
I mean, I think that's...
In fact, sorry, yeah. Go ahead.
No, go ahead.
I was thinking that is actually how Scratch and these other things do, isn't it?
Yeah, but they have a very simple, and they do not have the property that every subgraph of their evaluation graph is an evaluation graph.
Sorry.
Yeah, go ahead.
No, I was just going to say, so I think it's so the condition is not that every subgraph is an evaluation of an evaluation graph is an evaluation graph. I think what you need to impose is something that is quite analogous to what in graph transformation theory is called the convexity condition, where you want it to be the case that whatever subgraph you have, it must satisfy the property that any vertex that doesn't lie on the initial layer doesn't, you're not, when you take the subgraph, you're not severing any incoming edges. In other words,
Exactly.
the vertex incomponents to all vertices that lie off the initial layer are preserved under the action of taking the subgraph.
That sounds right. That's what I had in mind also, if you think of the partial order, I mean, sort of the DAG.
Right. So this is a condition that appears naturally when you're doing graph unfoldings and you want to take sub-evaluations of graph unfoldings. And yeah, it's a pretty general condition.
Okay, I understand the general concept of it, but
the basic idea is you shouldn't, your computation shouldn't be, your evaluation shouldn't be using dependencies that don't lie in the subgraph. I see. Don't use things that aren't defined in the subgraph. Right. So your initial layer, you're allowed to just generate that kind of from nowhere. But everything subsequent to the initial layer should only use things that are inside the subgraph. So none of those vertices should have incomponents that are changed by taking the subgraph.
Right.
The out components can do whatever they want, but the incomponents have to remain the same.
Right, but I mean, it's like when you disembody the thing, it cannot be the case because the evaluation graph has a notion of time, whereas sub-expressions do not have a notion of time. So you can pick up any sub-expression and it's a meaningful thing. It just sings and dances on its own, so to speak. But as soon as it's in an evaluation graph, there can be, it's like, I don't know what that is unless I got it from a previous state. Is that a fair assessment? In other words, a piece of the graph is simply not defined unless, whereas in an expression, it is what it is. It didn't have to be created. In an evaluation graph, things had to be created. And maybe there's a way of cauterizing it, of saying this is, like in sort of some general relativity kind of thing, this is a thing that's coming in from, I don't know, past infinity or something. Something that's just arriving, like you were talking about the initial layer just arriving. You're saying you can't guarantee that something not on the initial layer is well formed if it wasn't created by something. Is that a fair characterization?
Yeah, something like that.
But you could imagine preparing something that you could imagine sort of ex machina. No, that's really bad. For what we're doing. I mean, it could have just existed at the beginning of the universe type thing. You could, so long as it is well formed, it's okay to just plug it into the graph even later on. It's just that you don't anticipate that it will be well formed. Is that a true statement? I mean, there's nothing wrong with plugging in an intermediate expression that you didn't in fact get, that's a fake intermediate expression that you didn't get by actually constructing it. So long as it is correctly formed, I believe you can do that. Unless maybe it's go ahead.
Well, maybe for token-event graphs, it's easier to imagine. It's like preserve the events, only the inputs for events. You can drop any output, but the inputs to the events you always preserve, all of them.
Well, you're saying because otherwise the causal relationships don't work and so on. Right. We should wrap up here. Tony just sent. Oh, Tony. We didn't know Tony was here, but Tony just sent an example of the problem. Okay. So what the heck is this? Okay. X blank goes to function. I see. Yes. Okay. That's where it has to rename.
So that reminded me of RDF and Sparkle, where there are so-called blank nodes. Those are nodes which can't be referenced by definition from the outside. So this goes in the direction of pure, formal variables.
I see. Okay, so this is Jonathan, you were just commenting about expression manipulation internally in the theorem proving framework for quantifiers. What's that about?
So
I think that implicitly, when we give a variable or pattern variable, we think of it as for all.
right. So the point is that the theorem prover treats any universally quantified variable as a pattern, exactly as Roger said, and vice versa. When you're dealing with patterns in constructs, when you translate them back into statements, we put universal quantifiers around them with the appropriate scoping. And so there's already, in a sense, there's already functionality in the theorem proving framework for doing some manipulation of pattern expressions, for converting pattern expressions to ordinary expressions, and doing things like, you know, scolemization or changing bound variables or whatever. And then, as you mentioned, so dummy variables or dummy indices in tensors or something, that's a special case of that, where instead of just universally quantifying, you're summing.
Yeah, they're both quantifiers. Sum is basically a quantifier.
Right, exactly. But it's, yeah, as I mentioned, it's a special case of the above.
You know, it is quite head spinning how much how many common themes there are between all these different areas. Really remarkable. And we are, you know, that's where, you know, in the whole language design thing, this is where we'll get, if we can figure out this evaluation graph thing, there's going to be amazing power from that. And if we can get, because that is the next, that's sort of a, you know, it's a meta level of yeah, of all this stuff. I mean, you know, it is the more dynamic version of okay, the thing we have never metaized, no, we have never made symbolic, is the process of evaluation, so to speak. We've made symbolic so many things in our system, but the process of evaluation has not been made properly symbolic. And what this is about is making symbolic the process of evaluation, I think, which is something which, in a sense, in the physics project, a lot of what we can think about that as doing is making an actual structure that is the structure of space-time, et cetera, that is a representation of an evaluation process. Whereas, yeah, and anyway, okay, very interesting stuff. Well, look, thanks a lot, everybody, and we will continue this and try and, I think maybe, I mean, I felt like this was a, I mean, although we went through various different areas here, I thought this was a somewhat coherent meeting. I don't know how other people felt about it, but I think we're making progress. And you know, if anybody can think about this evaluation graph question, that would be really nice. Any last comments? Okay, sounds good.